Good morning, everybody. Good morning, dear candidate. Hereby, I open this academic ceremony in which Emilie Anduran will defend the academic thesis Bioreductive activated prodrugs to target tumor hypoxia. May I invite you to present a summary of your study and the conclusions of your thesis.
Thank you. So, dear Prorector, dear member of the Corona, dear audience, thank you for being here. In the next 15 minutes, I'm going to present you the content of my PhD project entitled Bioreductive activated prodrugs to target tumor hypoxia.
Please speak into the microphone or bend the microphone. Yes. Thank you.
So let's start with the introduction. Hypoxic tumors are solid tumors with an abnormal development of blood vessels and so a low oxygen supply. The consequences of this hypoxic tumor are an important aggressiveness, an important progression, the resistance to conventional treatment such as chemo, radio, or immunotherapy, and so a poor patient prognosis. For these reasons, it is necessary to develop new treatment strategies, such as, for example, hypoxia-activated prodrugs. The purpose of hypoxia-activated prodrugs is to selectively generate drugs in the hypoxic tumor environment by undergoing a bioactivation thanks to the action of one or two electron oxidoreductase enzymes upregulated in the tumor environment. As you can see here in the example of evofosfamide, in normoxic condition, the prodrug will undergo a one electron reduction to form the intermediate, which will be oxidized back in the prodrug initial form, while in the hypoxic environment, this intermediate will be able to undergo further reduction or fragmentation in order to generate the cytotoxic payload in tumor cells. Therefore, we have selected carbonic anhydrase 9 inhibitor as chemotherapeutic agent because CA9 plays a key role in hypoxic tumor cells. Indeed, upregulated, CA9 induces the acidification of the extracellular matrix, leading to its degradation and promoting tumor proliferation. We have also selected immunotherapeutics, so more precisely, Toll-like receptor agonist and Abertans tyrosine kinase inhibitor in order to reactivate the immune system to attack tumor cells through a natural process which is evaded during tumor proliferation. So the aims of this thesis were to synthesize and to do biological evaluation of carbonic anhydrase 9 inhibitor hubs, to synthesize and to evaluate new immunotherapeutic hubs, and to design and synthesize a new immunotherapeutic hub for antibody hub conjugation in order to improve the tumor targeting. So at first, we have synthesized and evaluate carbonic anhydrase 9 inhibitor hubs. These hubs are composed of two parts, a hypoxia-sensitive trigger and an active drug. So here, benzene sulfonamide compound, connected to each other by a carbamate linker. Two synthesis pathways have been used here in order to form 7 hubs. The first synthesis pathway is composed of 2 steps. So the first one corresponding to the activation of the bioreducible trigger using phosgen, then followed by the coupling of the active drug. 5 hubs have been obtained here using this pathway. Then the second synthesis pathway is composed of only one step, comprising first the activation of the bioreducible trigger using carbonyl diimidazole, followed then by the addition of the active drug in order to form 2 other hubs. We have then performed an inhibition assay on this compound using 3 different carbonic anhydrases, so 2 cytosolic, CA1 and CA2, and 1 intermembrane, CA9, in order to evaluate the inhibition activity of the compound in terms of affinity and selectivity. Affinity corresponding to the highest inhibition activity toward the targets, and selectivity corresponding to the highest inhibition activity toward a specific target compared to the others. Here, we observe that compound bearing the aminoethyl benzene sulfonamide active drug show the highest inhibition activity towards CA9, and more precisely that compound 1B and 4B show the highest inhibition activity combined to the highest selectivity towards CA9, as you can see here in the table. Then we have performed a toxicity assay on zebrafish larvae using 3 compounds, 1B, 4B, and 5B. Here we observed that compound 1B was the less toxic, with no abnormality observed on the zebrafish larva compared to compound 4B and 5B, which induced, for example, absence of swim bladder or formation of edema. We have then performed a viability assay on 1 compound, 1B. So we observed on HT29 cell line no cytotoxicity effect under normoxic condition, here in blue, but we observed here in orange a cytotoxicity effect, as expected, suggesting the enzymatic bioactivation of the prodrug. A similar profile has been observed also in another cell line, HCT116, but unfortunately, on clonogenic assay, 1B didn't reduce cell survival under normoxic or anoxic conditions. So then next, we have synthesized and evaluated new immunotherapeutic hubs. So as previously, these hubs are composed of 2 parts, the hypoxia sensitive trigger and an active drug. So here, toll-like receptor agonist, the imiquimod and the resiquimod, and a Breton tyrosine kinase inhibitor, the ibrutinib. A 2-step synthesis pathway has been used here in order to form the hubs, comprising first the activation of the bioreducible trigger using desuccinimidyl carbonate, followed then by the coupling of the active drug. During this synthesis, we encountered several solubility and reactivity issues in order to form these hubs in a reproducible yield, and also in order to form the compound 16 and 22. Then we have selected 2 other hubs, 18 and 20, in order to perform viability assay. Before to start the assay, we have performed an LCMS analysis on 18 in order to evaluate its degradation. And we observed 40% degradation by decoupling of the active drug, so the resiquimod. So then we have performed the viability assay using the resiquimod to compare the cytotoxic effect. We observed here in blue a cytotoxic effect in normoxic condition of 18, which can be explained by the presence of the residual resiquimod with the prodrug, while under anoxic condition, we observed higher cytotoxicity effect, which can be explained by the activation in the anoxic environment of the prodrug, which can be we can observe also in anoxic condition a low cytotoxicity effect of the resiquimod, which could be explained by the upregulation of efflux pump, which would pump the drug out of cells. Unfortunately, due to a too important degradation of the other compound, 20, we didn't observe relevant cytotoxicity effect. Then next, we have designed and synthesized a new immunotherapeutic hub for antibody-hub conjugation in order to improve the tumor targeting. So this hub is composed of 3 parts: the resiquimod as payload, the nitroimidazole as bioreducible moiety, and the linker allowing the connection to a tumor-specific antibody. This hub has been designed in order to be activated in the hypoxic environment by undergoing an enzymatic bioactivation, following here a self-immolative mechanism, in order then to release the drug in the hypoxic environment. So therefore, we have designed a 7-step synthesis pathway, comprising first the coupling of the linker, followed then by the coupling of the bioreducible trigger, and then the coupling of the active drug, so the resikimod. After this step, we observed degradation of compound 7 by decoupling of the drug, which prevented the obtention of the final compound 8. But in parallel, we have designed a second hap based on the same structure than the previous one, so comprising the same 3 parts, but connected here to a different central molecule. So here as well, this hap has been designed in order to be activated in the hypoxic environment by undergoing an enzymatic bioactivation, following also a self-immolative mechanism in order to release the resikimod in the hypoxic environment. So here we have designed a shorter synthesis pathway comprising 5 steps, and starting with the coupling of the bioreducible trigger, followed then by the coupling of the linker, and then the coupling of the active drug. So we observed here as well a low degradation of compound 16, but we succeeded to obtain the final compound 17 in order to continue then with the antibody conjugation. For this conjugation, we have selected cetuximab as antibody because of its affinity with a receptor highly expressed in aggressive tumor. So to do this conjugation, we have chosen a 2-step synthesis pathway. So starting first by the activation of the carboxylic acid function of the hap, and followed then by the coupling of the antibody using its lysine residues. Despite the different conditions tested, we didn't observe the conjugation, suggesting that another approach should be tested by first activating the lysine residue of the antibody, followed then by the coupling of the hap. In conclusion, we have synthesized and evaluated a carbonic anhydrase 9 inhibitor, which showed a potent selective inhibition activity towards CA9 under anoxia, with no toxicity observed, justifying to continue further study. We have synthesized and evaluated a new immunotherapeutic hap, which demonstrated an interesting cytotoxicity activity under anoxia, suggesting an efficient release of the drug in the anoxic environment. But the degradation observed will prevent to continue further study. And we have designed and synthesized a new immunotherapeutic hap for antibody-hap conjugation in order to improve the tumor targeting, but another approach needs to be tested in order to connect the antibody to this hap. So now I would like to thank you for your attention and to thank all the persons who helped me during this PhD. And now I give the word back to the prorector.
Thank you very much for your presentation. The opposition will be started with the chair of the assessment committee, Professor Sébastien Clément. He is from the ECGM, Institute de Montpellier, and I would like to ask him to start the opposition. He will be, as the other members of the opposition committee, of the degree committee, will be here online.
Thank you, Mr. Chair. First of all, I would like to thank Professor Guillaume Lubic-Benoit and Professor Philippe Lambin for inviting me for this PhD defense. So, dear candidate, thank you for this very nice presentation, which summarized well the subject and the main conclusion. So now I will ask the following question. So in the introduction, you mentioned several kinds of therapy, which are radiotherapy, chemotherapy, and immunotherapy. Did you know other kind of therapy which is maybe less invasive for the patient?
Thank you for your compliment and thank you for your question. Could you repeat, please, the end of your question about the different therapies?
Yeah, you mentioned in the introduction different kind of therapy, which are radiotherapy, chemotherapy, and immunotherapy. And my question is, do you know another kind of type of therapy which can be less invasive for the patient?
Which can be less invasive for patient,
Yeah.
right?
Yeah.
Other type of therapies, for example, hormonotherapy as well.
Did you know phototherapy?
Why right now?
Like,
Yes.
yes, like PDT or PTT?
No, I don't.
No.
Maybe not.
Okay, no problem. So we'll move to another question, which is about carbonic anhydrase inhibitors. So in your subject, you use sulfonamide inhibitors. Do you know how it interacts with carbonic anhydrase?
He's supposed to interact with the zinc atom in the active site of the enzyme, and and also it can interact as well with water molecule. Secondary, but mainly with the zinc atom in order to inhibit the enzyme.
Yeah, exactly. So do you know other kind of inhibitors? Because here, if you examine the selectivities, you have, it seems, no really selectivity between the different kind of human carbonic anhydrase. So do you know other family of inhibitor which can be more selective than sulfonamide?
So here we have focused on the family of sulfonamide, and I know sulfamate also,
Yeah.
family of compound. After here we have focused on this family of compound in this work, based on previous work.
What about coumarin or sulfocoumarin species?
Yeah, I know also this kind of compound. Yes.
And my question, do you know the different kind of interaction that you could have with the different type of inhibition or interaction with the carbonic anhydrase? Because, as you mentioned, first, sulfonamide can be used to interact with the zinc at the center. So, for example, is it coumarin interact in a similar way as sulfonamide?
In my work, I focused on the compound we used, so I didn't. I didn't. I focused on the working way of our family of drug. So I wouldn't know how to answer for the other family of compound.
Yeah, different kind of interaction. You can block, I would say, the entrance. You can have the interaction not directly with the zinc, with water, which is fixed on zinc, or you can have some interaction close to the site, which blocks some activities. Okay. Maybe one of my last question, two questions I finished. So for the nitroaromatics, when you make the reduction to the amino, how many electrons are involved in the in the reduction of the nitro group to the amino? Because in general, in the thesis, you didn't show exactly how many electrons are transferred or is needed for this reduction. Do you know formally how many electrons are involved in the reduction of the nitroaromatic to the amino?
To the how many electrons are involved? Sorry.
Necessary to make the reduction, in fact.
To activate hypoxia activated prodrugs, so there are two ways: one electron pathway and a 2 electron pathway, depending on the enzymes. So depending on the compound, it will be reduced by a 1 or 2 electron pathway. And after...
Yeah, I understand, but what is the oxidation degree of carbon?
This is not working. Please, one asks a question, one answers a question. Do not disturb each other, please. Technical announcement, please keep you on the rules.
Okay. Just to complete this question, what is the oxidation degree of the carbon of the nitro, and what is the oxidation degree of the carbon which is linked to the amino?
To the nitro.
Sorry, my question is not correct. The nitrogen, I would say. The nitrogen is the nitro, and the nitrogen is the amino. What is the oxidation degree?
I wouldn't know exactly now how to answer to this question, to answer exactly.
Okay. So the oxidation degree of the nitrogen in nitro is -3. It's not -3, it's plus, sorry, it's +3. And when you have the reduction, it is -3. So there is 6 electrons which is exchanged, in fact, in the nitro. Okay.
Yes.
So I will probably finish my question. So I turn it back over to the chair, and thank you again for your presentation.
Thank you. The opposition will now be continued by Professor Hane. His expertise is pharmacology of the Department of Pharmacology and Personalized Medicine of this university. Professor Hane.
Thank you, Prorector. Dear candidate, first of all, I'd like to compliment you with your thesis. You've performed a lot of work, not only synthesizing new compounds, but also testing them and determining their biological activity. A combination I like and which also forms the fundament of medicinal chemistry. You've also shown the perseverance, la persévérance, to go on even when success is not immediately there. And I'd like to compliment you for this. In these compliments, I'd like to also conclude the promotion team. The strategy you choose is elegant, targeting a drug to the tumor by making use of a specific characteristic of the tumor, namely the altered redox status, or to be more precise, the lower oxidative tension in the solid tumor. Now let's start some discussion. I'd like to start with a basic biochemical question. On page 12, you correctly state that in hypoxic conditions of a solid tumor, there is the Warburg effect. It means that glucose is metabolized to lactate. How much carbon dioxide is formed in this process?
Highly esteemed opponent, thank you for your compliment and your question. I didn't hear very well. Can you repeat your question at the end?
The question is that in the hypoxic condition, you have the Warburg effect, glucose is metabolized and how much carbon dioxide is being formed?
How much? How many carbon dioxide?
Yeah. So if you have one molecule of glucose that goes into the glycolysis in the Warburg effect, how much CO2 do you get?
I wouldn't know exactly how to answer specifically to this question. I know that in hypoxic condition, indeed, there is the glycolysis is really the glycolysis mechanism is really important for the survival of tumor cells, but exactly in detail, I wouldn't know how many molecules.
Glucose is C6. Yes, this goes to 2-pyruvate, C3, and the pyruvate goes to lactate, also C3. So you have C6 compounds giving 2 C3 compounds. So I would say there is no carbon dioxide formed. Do you agree?
I didn't hear very well. So I'm sorry, I didn't hear you very well.
Yeah. Okay, well, I don't know if there are some technical things I should do.
Oh, there isn't.
Oh, okay. No, so C6 goes to 2 C3 moieties, to lactate. So there's no CO2 being formed. Yet in your strategy, you target the carbonic anhydrase, which uses CO2. How is this possible? Is this logical? If there is no CO2 or less CO2 formation by glycolysis, is this relevant then?
I know that in the hypoxic environment, the carbonic anhydrase present in the external part of cells catalyze the CO2 hydration, and then it's another carbonic anhydrase, the Ca2, which will in the cytosolic environment, which will do the reverse reaction in order to produce CO2, which will pass through the membrane to go out of cells, and it is going to form like a cycle reaction.
The key is shown in the EFP. That's correct. Perhaps I can ask a last question due to time.
A brief one and a brief answer, please.
Okay.
On page 37, you say that there's a lack of reliable biomarkers. So we need new biomarkers. What are the biomarkers you are thinking of?
We mean that we need to find more characteristic of tumor cell, of hypoxic tumor cell, in order to target them in a better way than what is done now. So we didn't specify a particular other way, but
could you use the concept also to target a biomarker?
Please repeat.
So my question is, could you also use the HAP concept to target a molecule to the tumor so that it can be used as a biomarker? Is this a good idea?
I don't know all the specific characteristic of hypoxic tumor cell, but The idea would be to target, the different receptor or highly expressed, for example, receptor present on hypoxic cell compared to normal cell, or to target different kind of receptors. Or
Thank you for the answer. I think we might discuss this perhaps later on, and I give the word back to the prorector. Thank you.
Thank you very much. Sometimes we have difficulty hearing each other because the connection is not always optimal. That's always a disadvantage of having an online meeting. But it is as it is. And I would like to continue the opposition with Professor Thibaudot, Professor of Chemistry, with a focus on superacid chemistry, fluorine chemistry, and bioactive compounds of the IC2MP Institute, Université de Poitiers. Professor Thibaudot.
Thank you, Mr. Chairman. First, I would like to thank the supervisor for the invitation to participate to this evaluation, external evaluation. And I would like to congratulate you, dear candidates, and your supervisor for the excellent quality of the work that is described in this PhD in a context that is really competitive domain. So I will have 4 questions, I would say. So my first one is a general question. Do you know which other type of proteins that could be targeted on the external part of tumoral cells that are upregulated compared to normal cells?
Highly esteemed opponent, thank you for your compliment and for your question. I know different, I know, for example, in antibody, in the tumor targeting antibody strategy, I know, for example, another receptor, the endothelial growth receptor, which is really highly expressed in tumor cell, and which is targeting by this antibody in order to treat tumor cells, to treat cancer.
Okay, thank you. My second question is a question of chemistry. When you generate it's in chapter 3, sorry. When you generate the N-alkyl O-alkyl carbamates, you do that in the presence of an alcohol and an amine, and sometimes you can use carbonyl diimidazole. And sometimes the yields are not excellent. I would say, for example, for compound 3B and 3C, the yields are less than 50%. So could you explain that? And could you give me some details about the mechanism of this reaction?
Yes, so 2 synthesis pathway has been used here because we have not done the synthesis in the same period. So first, the first synthesis pathway has been developed to form the 5 first compound, and then I have developed the second one in order to form 2 compounds more. So that's why we didn't use, for example, the same activation strategy. So your question was about which mechanism, which synthesis pathway?
Yes.
You ask me to precise a bit more the mechanism of the first one or the second one?
The one with the carbonyl diimidazole activation.
So the idea here was to first activate the bioreducible trigger, so using CDI, and after a few hours of activation, the idea was to do in the same step the addition of the active drug on the on the activated carbamate compound to couple the active drug. So the intermediate will be like the carbamate with the imidazole connected to it, to then make it react.
Maybe an isocyanate intermediate as well?
Sorry, can you repeat, please?
If you release the imidazole group, you generate an isocyanate intermediately?
Yes.
And so maybe it can be hydrolyzed. So I don't know, maybe it's something like that. I go to the third question because we have not a lot of time, so I'm sorry. Dear candidate, could you give me some comparison or some explanation to compare the compound 1B, for example, that looks very good, compared to another nitroimidazole containing HAP, like TH302 that you mentioned in the introduction of your PhD. Does compound 1B is better or as good than the other one? Because we do not see that in the PhD.
Yeah, with the evofosfamide, so this compound reached clinical trials already. So it's based on the same ID. So a nitroimidazole to target the hypoxic environment. But for the moment, in our case, we have just done cytotoxicity evaluation on tumor cells. So maybe we cannot compare already the two HAPs.
Regarding chapter 4, I have one question. There's some difficulty of synthesis due to solubility problems. You choose to link both groups with a carbamate linker again. Is it possible to directly link the imiquimod to the nitrofuran or nitroimidazole? And would it be possible to release the compound without losing CO2, without the carbamate? So directly the amine or alcohol to the imiquimod. Is it possible?
In this work, we wanted to keep the same releasing strategy. So using also a carbamate linker. So this strategy is really convenient because it allows the release of the drug, the active drug, just by releasing as byproduct a CO2 molecule. We didn't try to connect directly the bioreducible trigger to the active drug. Our objective was to synthesize on the same strategy, different type of HAP in this project.
Okay. My last question, if I have time.
I think we've passed the time. So if you have a very brief one and a very brief answer, otherwise we have to move on. Thank you.
Okay. Very briefly, the compound you targeted in chapter 5, they are racemic. Have you got an idea how to prepare them in a stereoselective manner?
And in chapter 5, can you repeat, sorry?
Yeah, you have racemic compounds because you generate a benzylic alcohol. You have a racemic mixture. Have you got an idea to generate the enantiopium one?
Maybe by a separation technique, maybe, I would say.
Okay, thank you. So I give back the discussion to the show. Thank you very much.
Thank you. The opposition will now be continued by Professor Jabluskis. He is a professor in organic and medicinal chemistry of the Latvian Institute of Organic Synthesis of the Riga Technical University. Professor Jabluskis.
So first of all, I would like to congratulate dear candidate for very exciting pieces of work which are combined in a PhD thesis with, it's not showing, but with a very beautiful design. So I will try to stay short and stick on 2 questions. I'm pretty sure candidate knows the answers. And first question is, what exactly reduces NO2 group in this compounds what you use for this immobilized on imidazole? Are those enzymes or some reducing species in the environment?
The opponent, thank you for your compliment and thank you for your question. Can you repeat, your question about the nitro?
What exactly reduces nitro group? Enzymes or reducing species, for instance, for example, thioredoxin?
It's so here it's to reduce the HAP. It's oxidoreductase enzymes, so more precisely nitroreductase. After, depending on the molecule, we have to find which specific enzyme which would reduce the molecule.
Thank you. I will ask second question that relates to the chapter, I think it was chapter 5, which is dealing with antibodies, and you are modifying and attaching via linker to antibody. I think it was cetuximab you mentioned in your presentation. And how do you judge how many of these molecules what you prepare will be linked to the antibody, considering that there might be quite many lysine moieties in antibodies? That's one. And second, would it or can it influence ability of antibody bind in a specific area of the cell?
Yes, exactly. For the moment, we didn't focus on the conjugation ratio, but we wanted to test different conditions in order to succeed to do this conjugation, even if we could conjugate several HAP on the same antibody. In the first time, we didn't focus on the ratio. We tried maybe to change the equivalent on the conjugation reaction in order to play on this ratio. But for the moment, we first would like to succeed to do this conjugation, and I think in a second time we will focus on to improve the ratio, the antibody HAP ratio.
Thank you. And how you would judge, just your judgment on this, if you have too many molecules of your compound linked to or conjugated to the antibody, may it influence its ability or affinity binding in the cell?
In my opinion, if too many HAP bind to the antibody, maybe it could be too active and maybe toxic. So I think we should try to control the ratio to avoid to have too much HAP connected on the same antibody.
Thank you. And I give back the floor to the chair.
Thank you. The opposition will now be continued by Professor Virieux. He is a professor in chemistry of the ECGM Institute, Université de Montpellier. Professor Virieux.
Thank you, Mr. Chairman. So, first of all, I would like to thank the candidate supervisor, Professor Lambin, Professor Jean-Yves Vinhomme, and Dr. Dubois, which success me as a jury member. And would like also to thank the PhD candidate because you performed a quite well and good presentation, and I also appreciate your manuscript. So my first question will be dedicated to the redox properties of your molecules. So if you can do some in vitro experiment, do you think it's possible to determine how you can proceed to check at what kind of redox potential you can have the release of your drug candidate? And what kind of experiments you will perform for that?
Highly esteemed opponent, thank you for your compliment and thank you for your question. So, in order to measure the exact reduction, in order to measure where exactly on, for example, an hypoxic tumor, the HAP could be activated, we could perform in vitro an experiment on a spheroid, for example, a spheroid model representing the hypoxic tumor, and expose it to the treatment, and then after, by cutting the spheroid by slice, we could then, on the slice, on the different area, we could measure the presence, for example, by the mass of the HAP, if it has been activated or not, depending on the reduction potential. For example, I would suggest.
Okay, this is one possibility. So it means that this is a biological regulation, and if you want to perform something which is more focused on chemical regulation of the release of the drug.
We could, so we could, for example, to test the activation of the HAP, we could expose it at different reduction potential, and observe, for example, after by a mass analysis, for example, if we can see still the HAP, or if we can see the active drug released after reduction.
And I will focus again on biomarker as a previous question, which was addressed to you by another member of the jury. So concerning the biomarker, what do you think? You may have two different solutions, you may express two different solutions to have the relation of the drug cleavage. So do you think that you could use carbon dioxide as biomarker, and what kind of carbon dioxide you may use?
Sorry, I didn't hear you very well. Could you repeat your question?
I can try. So you, in the way you proceed, you have the release of carbon dioxide, correct?
Yes.
And do you think that you can change a little bit the carbon dioxide by something else to have a precise evaluation of the release of carbon dioxide, but with some typical feature?
I didn't understand very well the question, but yeah, by activating the HAP, we produce a CO2 molecule, and you would like to, by marking the CO2, you would like, by using, by using an isotopic marker to form the HAP, and then to be able to follow it, to follow the release of the CO2.
This is what I would like to hear from you. Okay, that's right. So you can have a marked or labeled CO2. So that's potentially one solution. And if you want to check also by that way, not by the release of CO2, but the release of something else which can be easily detected in by any kind of procedure. What kind of marker would you use?
I didn't.
So the molecules, you have the nitroimidazoles. Then you have the release of CO2, which is the link between your HAP and your redox part of the molecules. And then you have the HAP by itself. Can you change the HAP by something else just to be sure that we are releasing the compound you may have?
By the HAP, what do you mean?
Your drug directly. So can you release something else than your drug?
Sorry, can I? The question, can I?
Can you release something else than your drug, which can be detected by any kind of procedure?
Understand. Sorry.
We have a bit of difficulty in hearing you. It might be the connection, so could you repeat your question, please? Or even alternatively, it could be in French to make it easier for the candidate and for us to understand. So maybe I suggest you switch to French, and then we continue in English.
Okay.
Okay, I'll switch to French just briefly. Quand vous libérez votre molécule, à partir du système nitroimidazole, donc on a la libération de CO2 et la libération de la molécule active. Est-ce que cette molécule qui est libérée pourrait être quelque chose d'autre qu'on puisse détecter facilement?
Vous parlez de la drogue?
De la drogue. Donc là, je ne veux pas quelque chose qui soit la drogue, je veux quelque chose qui soit autre chose.
Après, can I answer in French? In English. Okay.
English, thank you.
So the HAP concept is to be able to adapt on every kind of therapeutic compound this strategy. So to connect, the idea is to connect on every therapeutic compound a hypoxia sensitive trigger, which would deactivate the drug and only activate it in the hypoxic environment to release the active drug and avoid also reverse effect on normoxic cells. So I don't know if I understood very well your question, but we could replace the active part, the drug, by another one. Here in this project, we have worked on different kind of therapeutic, but yeah, this idea could be adapted to other active compound.
That's correct. You can adapt the molecule which is released by other type of drug, but the main idea, if you branch in your system something which could be fluorescent or not, just to check if in the proximity of the tumor you have the release of your drug. Do you think it could be possible?
Yes, it's also possible to do imaging by using this technique and replacing, yes, the active drug by a fluorescent molecule, for example, to visualize the tumor, the hypoxic tumor.
Okay. And my last question, if I have the time, would be on ivofosfamide. So this is nitrogen mustard. So do you think that this is truly a prodrug, or is the molecule by itself with the nitroimidazole is active at all?
So on which compound are you talking, sorry?
The compound with phosphorus moiety.
Oh, okay. So you asked me if it's really a prodrug, or yes, I would say yes, because it needs to release the DNA cross-linking agent to be to act on tumor cells. After the idea here, it's by connecting the nitroimidazole, it's to increase the targeting of the tumor and to decrease the reverse effect, which could be done on normoxic cells. So yeah, I would say it's a prodrug because it needs an activation.
Okay. So anything you can take from your question? And would like to invite you.
Thank you. The opposition will be now continued by Dr. Rauschop. He is an expertise in biology of the Institute of Department of Radiotherapy of this university. Dr. Rauschop.
Thank you very much. So first of all, I would like to congratulate you with your thesis. I think it's a very nice piece of work. You've shown lots of well-executed experiments that yielded lots of new compounds, and you also addressed this in biological assays. So despite being a chemist, you seem to be very much at ease with biological techniques, when that's not always the case. So I also tend to agree with your proposition 8, that you need to have at least some understanding of chemistry to fully understand biology. You don't have to look it up. I will not ask a question about that, but I really liked your proposition. So I'm very brief and very quick because we only have very few minutes left, so I'll immediately go to the questions. So in chapter 3, you've created these HAP CA9 inhibitors, and in the introduction and also the overall introduction, you very nicely described that CA9 is an attractive target because it's hypoxia regulated, it's already hypoxic specific. So why do we then need a HAP CA9 inhibitor if it's already hypoxia specific?
Highly esteemed opponent. Thank you for your compliment and thank you for your question. So you are asking me why we need.
If CA9 by itself already indicates hypoxia specificity, so it's only upregulated in hypoxic regions. So why do we then need a drug, a CA9 inhibitor that is also specifically targeted to these regions? Because otherwise, so if you don't target it, it will end up there anyway, or.
We use the HAP strategy. We have synthesized a HAP with a carbonic anhydrase 9 inhibitor in order to focus the action of the HAP on the hypoxic environment, on the inhibitor on the hypoxic environment, and to decrease any other action of the inhibitor on normoxic cells, because carbonic anhydrase 9 are also present in healthy cells.
Okay.
So it would be to target specifically.
Okay, thank you. Yeah, that was not described in your introduction, but you're correct. So, and if I then may ask a couple of very specific questions on chapter 3. So, for example, you've created all these compounds, And then you start testing their inhibitory capacity. So table 1 I refer to now. And then in the end, you will select compound 1b, right? So, but I was a little bit surprised by the assay that you performed, because this assay is performed during non-Maastricht conditions. Or am I mistaken? So the results that you present in table 1,
yeah,
the assay was done during non-Maastricht, right?
Yeah, under non-Maastricht condition and also under anoxic condition.
Is it also an, oh, okay.
By using...
In table 1, you mean?
Ah, sorry.
That's just the inhibitory values, the Ki values of your different compounds.
Sorry.
Can you answer briefly?
This evaluation have been done on non-Maastricht condition, and so your question where?
Yeah, I think we have to continue this discussion afterwards, because I still have some additional questions on this table.
Okay.
But in view of time, I think I will give back the word to the prorector.
Okay.
Thank you. That's always what good research ends into, further discussion. Emilie Anduran, the time appointed for defending your thesis has passed. The degree committee of both l'École nationale supérieure de chimie de Montpellier and the University of Maastricht will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes. In the meantime, let's take a closer look at Maastricht University's renowned teaching method, problem-based learning. Once the prorector reconvenes the session, we'll tune in and continue the live stream.
Problem-based learning, or PBL. What does that mean exactly? 3 of my fellow students and I will show you around. Every week, we analyze a different case or issue together. We discuss the case and everyone can contribute different perspectives to the group discussion. If we get stuck, our tutor helps us out and suggests what we could do next. I prefer going to the library to prepare. Here, I can focus and I have quick access to books or journals that help me understand the case. Today, I can also train my stitching skills in the Skills Lab, where you can immediately put into practice what you've learned. After a day like this, I like going to the gym to clear my head and get ready for the next day.
At UM, you meet people from all around the world. Hello guys. Some of them are doing their exchange semester here, and they often say that PBL helps them learn and retain things very easily. I can understand why. It's a very active way of learning because you have to bring your own perspective to real-life cases. You have a lot of freedom to manage your time, your studies, your hobbies, and your work. Of course, that also means a lot of responsibility. Right now, for example, I'm arranging my exchange semester in Madrid. How cool is that? In this group session, we're the managers who have to allocate the resources of a real company. This is how we put into practice what we learned this morning. Studying here means being proactive and learning to plan well. Prioritizing and performing well under stress are great skills that help you develop as a person. But now, it's time to grab a coffee at the Student Service Center.
Right now, we're at the Brightlands Camelot campus. Here we can apply knowledge from lectures and tutorials in a practical setting. This helps us understand what we have learned and further develop our lab skills. Today, we're determining the amounts of cholesterol in various products. What I really like is the project periods at the end of each semester, where we complete a full research project. That includes planning, collecting data, analyzing, and presenting the findings. That way we learn how research works and we're able to see what it's like to be a real scientist. After practicals, I have to write a lab report that also helps me process everything I have learned today. has a lot of learning spaces where you can work on your own or with other students. This evening, I'm meeting my friends for a movie night organised by the MSP Study Association.
If you study law, you have to read quite a lot. Not all information is relevant, so you learn how to easily find the information you need to solve your case. In the afternoon, I have to give a presentation, so I like to practice it with a fellow student. Later today, a lawyer is giving a lecture. This will help us better understand the case we're working on. Speaking in front of a group is quite exciting the first time round, but you get to used to it quickly. And having to present helps you also to adopt knowledge better. What I like the most is that we sometimes get to enter a plea in front of a real judge. These moot courts are really exciting. Now it's time for drinks with friends. Studying is important, but so is relaxing once in a while.
Emilie Anduran, the degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee of the Maastricht University and l'École nationale supérieure de Chimie de Montpellier has decided to grant you the degree of doctor. Professor Lambin and Professor Wienem are authorized to confer upon you this academic distinction in accordance with Dutch and French university custom. I invite your superiors now to take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Emilie Anduran, the degree of doctors and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificates signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. For the sake of clarity, I give you here a doctorate diploma from both Maastricht University et l'École nationale supérieure de chimie de Montpellier. I now give the words to your supervisor of Montpellier, Professor Wienem.
Thank you, Philippe, Mr. Prorector, dear member of the jury, dear colleagues, dear public. So it's traditional for the supervisor to highlight certain characteristics of the candidate or to tell some anecdotes. So I will try to do both. First of all, I would like to congratulate you for all the work that you did and for this defense in English, yes, which is not so easy when it's not your mother language, and this defense in English that have made you tremble for almost 1 month, yes, 2 months. So you have done a lot of work in the last few years, and you have been able to evolve positively as a researcher, but still complaining. I'm not sure it's the great word in English. Maybe it's grumbling, as much as when an experiment was not working. So I can tell you, for example, in French, bouh, mais pourquoi ça marche pas? Oh, je comprends pas. Oh, c'est pas vrai. So in English, oh, that's not true. Why it's not working? So this is Emilie. But we like her, like she's like that. So this last year have not been as easy as expected. Of course, there was a COVID period. Okay, a few months of lockdown. That fortunately, you did not give you the desire to do chemistry in your kitchen. Then we had the move of the lab to another building in Montpellier. Packing, unpacking, tidying up, cleaning, especially all the leftover silicone bath that you broke. At least 4 liters spread in the lab. Anyhow, thank you again for all your great help during this move in, this move out, and this move in. And let's go to the anecdote, maybe. For someone who is coming from the region where D'Artagnan was born, D'Artagnan, the musketeer, understand? And who is defending her thesis in the city where D'Artagnan ended his life, I think the story was not so bad, I mean.
Yes.
But however, the story with Maastricht has started very badly. The first memorable visit was quite tough for you and for Ludwig too. who both had your laptop stolen in the Ludwig car. In fact, Maastricht is worse than in Montpellier. And for Emilie, it was a loss of 6 months of data. Let's see the positive side of things. I mean, you visited the police office of Maastricht. This is good, I mean. Moreover, the good thing was that she decided to have a cloud and to buy an external drive, which is essential for researcher.
Yes.
So I will finish by congratulating you once again. It was a real pleasure to work with you during these last 4 years, because you spent 3 years in Montpellier.
Yes.
Yes. And I wish you all the best for the future and for the next steps.
Merci.
Thank you again.
Merci.
So, dear Emilie, also congratulations from my side. This is obviously the advantage of having a double degree.
Yeah.
That both of us can say something. So we got a challenging task, making from a chemist a biologist in, well, let's say a bit more than 6 months. So I all want to share with you how that works. How do you make from a chemist a biologist? So this is a recipe kind of idea. So an important thing that Emilie needed for her research in biology was to learn how to do tissue culture. So usually somebody gives you a T25 flask, gives some explanation on you pipe it a bit of that and you pipe it a bit of that, and shows you how to do continuous cell culture. The first challenge is, of course, is how to culture without any bacterial contamination. But I have to admit, Emilie was very proud that she could do that indeed without having contamination in a T25 flask. So we decided, okay, let's move on to the next step, make it a bit more difficult and do cell experiments in a 96 well plate format, essentially to test the efficacy of your compounds. So that's the research question behind that. But then suddenly Emilie realized from, oh, a T25 is not a 96 well plate. It's a bit more complex, a bit more time consuming, because you need to count cells, you need to make dilutions, you need a hypoxic chamber, you need to seed much more wells, and then you also have your first contamination. Yeah. Shit. So you have to start again from scratch. This is that's not turning a chemist into a biologist, because with all the people sitting there, they experience that as well, so no worries about that. So biology became a bit more difficult than anticipated, but let's be honest, with the help of others, a lot of people in the lab, and you have indicated them in your acknowledgement, so you succeeded to perform several of these biological experiments. Now the question is, are you now a biologist? Well, I think it depends on who you ask. For me, you're a biological chemist, which I see personally as an advantage. But like you said in your proposition 8, and that has been referred to, there's no true understanding of biology without chemistry. I think you should turn this around and make there's no true understanding of chemistry without biology. This you have proven by the contacts you have made with the biochemistry department to actually help you out with antibody coupling, which, okay, that's science, which was not successful, but I think it made you thinking it or considering it from a biological point of view. And how can you actually adjust chemistry based on biology? So I would reverse your proposition number 8. Well, but there's an advantage of being or becoming experts in both fields. So from our discussions at least, now I do understand what nitrothiofen is and what DCM is, so dichloromethane. However, and now I'm going to take a risk with all those chemists here in the room. I don't understand why you use these complex phrases as 1-methyl, 2-nitro-1-H-imidazole, 5-il-methyl, 2-etoxymethyl, 1,2-hydroxy-2-methyl, propyl, 1-H-imidazole, 4,5-C, quinolin, 4-il-carbamate. Jesus. Well, I'm happy at least that as biologists in the lab we could use hap-rezikimot, or EA1112, or EA281. By the way, what I just said, this is compound 18 in chapter 4, if you would like to know. So why not just call it compound 18? That makes our lives, and I think everybody's lives, a bit more easy. But anyhow, so I consider you as a chemist with increasing knowledge in biology. So I hope you had fun in Maastricht and have learned a lot, also from the Dutch side. Congratulations with obtaining your double degree, and I wish you good luck in your further career.
Thank you.
Dear Dr. Anduran, also on behalf of the Maastricht University and l'École nationale supérieure de chimie de Montpellier, here again you see the difference in the length of the title, je voudrais vous féliciter avec votre degree. Now I switch back to English because this is a unique ceremony, at least for me, being
Merci.
both in French and in English. I would like to congratulate you with the doctorate acquired. And during when we discussed the quality of the defense, I have to admit that I, on behalf maybe of the University of Maastricht, apologize for sometimes that our connections were suboptimal with this Zoom online defenses. It's always worse than having a real life defense because, like it's already said, hearing chemists saying something in a different language with all these abbreviations. I'm a simple endocrinologist, but I couldn't understand 50% of it. So I'm quite happy that at least you could understand 80% of it, given the quality of the connections. So we all congratulate you. And after the ceremony, which now will be finished, there is a reception outside in the garden, and thereafter we call it. I would like to ask the degree committee to remain in this room so we can, they can congratulate you, and afterwards there will be a brief photograph sessions. And hereby I would like to formally end this academic session.
We have to, yeah.